We consider collision where a ball with some mass, not unspecified, moving at 4 meters per second collides with another ball with half again as much mass, which is initially at rest. Now, let's define an elastic collision and test whether under certain circumstances this collision is in fact elastic. Okay, well, in an elastic collision, kinetic energy is conserved. That means the total kinetic energy of the two objects before the collision is equal to the total kinetic energy after the collision. Now, of course, you have impulse momentum, and this is an idealized collision where the net force is just the interaction force between the two masses. Well, let's suppose now that the first ball, the collision is such that the first ball comes to rest, and the second ball then continues on with some velocity. We can determine what the velocity of the second ball is going to be because we can apply the impulse momentum theorem. We can then determine whether the kinetic energy is conserved. So, because we can calculate the kinetic energy after collision. Now, of course, we don't have a mass, so we can't actually calculate the kinetic energy, but we can calculate the velocity of this ball after collision, and we can calculate the ratio of the two kinetic energies. Turns out that it doesn't matter a bit to answer these questions what the two masses are, as long as this one is half again as great as this one. Okay, so we answer these questions. Okay, first of all, what impulse brought the first object to rest? Now, again, we're assuming the first ball comes to rest as a result of the collision. So how can we determine the impulse that brought it to rest? And then what's going to be the velocity of the second ball, and finally, is kinetic energy conserved? Now, naturally, we would want you to think of these questions if we just asked you the question of whether kinetic energy was conserved or not, but this is how it can be broken down. So, we're going to let M1 and 1.5 M1 be the masses. We're free to choose any mass we wish. We could choose some specific mass, 200 grams or whatever. But then we wouldn't be sure that whether our result depended on that mass or not. So we're going to use symbolic expressions for the masses. And this one has to be half again as big as this one, 1.5 times this one, so this is the way we're going to do it. Now, one person chose M sub 0, M naught, and that's a fine choice, but when we get into special relativity, M sub 0 is going to refer to rest mass, and it kind of connotes that, so I prefer not to use M sub 0 except in that context. And it would be, excuse me, I certainly wouldn't penalize it, but it'd be kind of a good idea if you avoid using a subscript 0 with mass for that reason. And if you forget that, it's no big deal. Okay. Okay, anyhow, let these be the masses, then what's the impulse on the first ball? Well, people were kind of hesitant here. We've only been talking about this for a week. Impulse momentum theorem says impulse is equal to change in momentum. Okay? So all we have to do then is find the change in the momentum on the first ball, and that's going to equal the impulse. Now, I digressed to rederive or indicate most of the details and certainly the idea of how we derive for a constant acceleration situation the impulse momentum theorem and work energy theorem, basic work energy theorem. Okay, so okay, if acceleration's constant, then we do an integral and so forth, and we get, or analyze a trapezoid because the v versus t graph is linear. Either way, we get Vf equals V naught plus A delta t. And then, if we got the net force, acceleration is net force divided by mass. Replace acceleration by net force divided by mass, and we rearrange the equation to get F net times delta t, Well, to get F net times delta t, we multiply through by m, and then we take the mv naught here over to here, and we find that F net delta t is change in mv. Now, that's very simple, and you really should be able to derive that because it helps reinforce how everything is related. And then we did the same thing basically for work energy, okay? And there we derive the idea of work energy is equal to the change in 1/2 mv squared, which is change in kinetic energy, just from the Vf squared equals V naught squared plus 2a delta S. Okay. A is just F net over m, so we do the same replacement and we rearrange things and we end up with this. We get our F delta S over here, F net delta S over here. We get a 1/2 m Vf squared minus 1/2 m V naught squared on the other side. That's our change in 1/2 mv squared. Okay, well, back to this. Okay. From understanding the impulse momentum theorem, we understand that impulse is equal to the change in momentum. And we can calculate the change in momentum of this object because, at least in terms of its mass, which we symbolize by m1, because we know its velocity before the collision and we know its velocity after the collision. Okay, so the impulse, which is equal to F net delta t, in this case is equal to m delta v, where m is the mass. And the mass being constant, notice we have a delta of mv here. If the mass isn't constant, then you have to take the changing mass into consideration. But if mass is constant, it just factors out of the delta mv, which is just mvf minus mv naught. You factor out the m, and you get m delta v. So there's our m delta v. Okay, that's our impulse, and since we know delta v, we're going from 4 meters per second to 0. Delta v is negative 4 meters per second. The impulse is m1 delta v1. Delta v1 is negative 4 meters per second, and that's times m1. So there's our impulse. Now, what will be the velocity of the second ball? Well, the impulse on the second ball has to be equal and opposite to the impulse on the first ball, under our assumption that the net force, the only forces involved, the net forces are equal to the interaction forces between the two balls. Newton's third law says that those forces are equal and opposite, and certainly they act for the same duration of time. Now, they're not constant forces, so strictly speaking, we haven't established that either of these really applies in the case of a non-uniform force, which would lead to a non-uniform acceleration. I comment that this is acceptable right now, and just take my word for it. But if you really want to know, work it out, that you get the same thing if you do the integrations, the relevant integrations. So the net result is still the same. So this is still valid, and the work energy theorem is still valid. In any case, okay, by Newton's third law, the forces are equal and opposite, so the impulses are equal and opposite. That means that the impulse on the second object, and we don't care about F net and delta t, but it's, in this case, it's m2 delta v2. We do care about F net delta t because Newton's third law is what tells us that F net delta t is equal and opposite, so that the changes in momentum are equal and opposite. So our change in momentum, m2 delta v2, is equal to the negative the change in momentum of the first, or negative the impulse of the first. And that impulse was negative 4 meters per second times m1. So it's the negative of that negative. And then we very easily determine delta v2 to be 4 meters per second divided by m2. 4 meters per second times m1 divided by m2, just rearrange the equation. And m2 is 1.5 m1, so here is our delta v for the second object. So that the delta v2 is 4 meters per second times 2/3, because m1 divided by 1.5 m1 is 2/3. You can work that out if you have to. So there we have it, and then we can easily see what the velocity of the second after the collision will be. Initially, it was 0. The change was 2/3 of 4 meters per second, so the final velocity will be 2/3 of 4 meters per second. Now, we'll get to the changes in kinetic energy, but this particular video is getting a little bit long.